Okay, well, thank you all for coming. It is my great pleasure to welcome our speaker today, Geha, who's coming from Yale, our second visitor from Yale reporter. Marla is extremely prestigious. She's won, I think the only person I know has won prestigious postdoctoral fellowships in 2 countries. So the Hubble Fellowship here and the CASS in Canada. But she took that out of Victoria, which is not a good serve. Very cool. Since she's gone back over at Yale, she's also earned the Sloan Fellowship. She's been named on the Whitney Humanities role, which is impressive for scientists to be awarded for humanities things, which is really great. And I think the most amazing thing is that she's also been named the Brilliant 10 in Popular Science, which is probably why if you go on Amazon, you can find a full wall picture that you can order for $170 to put in your living room.
I'll give you a discount price.
All right. She did her graduate degree at Santa Cruz, where she was also distinguished there with Whitford Prize and Presidential Dissertation Fellowship, and only got the 45+5 at UCSC. So apparently they're not as selective there. Dr. Geha's work is focused on near-field cosmology, mostly dwarf galaxies, so satellites around major galaxies like the Milky Way, ultra-faint galaxies, and by studying these systems, she can actually measure the entire mass function of these different galaxies. Something we can't actually do very well here in the Milky Way, so she's actually learning about the stars and the systems in a much more precise and fundamental manner than we can do here in our own system. So today she's going to be talking about quenched dwarf galaxies in the field. Please take it away. Thank you very much.
So I'm delighted to be talking in the Marlar room. I think that seems appropriate. Just take one letter off.
I told her if you gave us $5 to change.
This is how I change slides?
Yeah.
Good. Okay, thanks. So it's a pleasure to talk to you today. I've had some great interactions today already. I'm going to be discussing something actually more massive. I like dwarf galaxies. I study lots of dwarf galaxies. I often talk about very, very low mass galaxies. So the satellites around the Milky Way, and particularly the ultra-faint satellites around the Milky Way, things that are these tiniest galaxies in the known universe. Today I'm going to be talking about a little bit more massive dwarf galaxies. That's maybe not small driver. Galaxies that are sort of the mass of the Magellanic Clouds or a little bit smaller. And I'll be talking about some work that we published just about a year ago, and then some follow-up stuff in the last year. So the last half of the talk is super preliminary, which is always fun and kind of dangerous. The first half of the talk is completely summarized in my title, so I should just be done and I'm gone. We found that there is an absence of quenched galaxies. That is, there's an absence of things that are not forming stars in the field. That is, if you go out into isolation and you find a dwarf galaxy, it is always forming stars, which is a fairly interesting result. And so my hope is that I can convince you of that, at least in the first half. The innovation, or the reason that this work was able to be done, and it hasn't been done before, is not that these dwarf galaxies are difficult to find. In fact, we see 10,000 low-mass galaxies in the Sloan database. The problem is that in the Sloan Digital Sky Survey, it just wasn't, the data pipeline was not optimized for nearby objects. And so if you go into the Sloan database and you ask for a bunch of dwarf galaxies, this is not a dwarf galaxy, this is a massive object, all the blue circles are different photometric objects. And so what's happened is the pipeline has decided that this large massive galaxy is broken up into a whole bunch of different pieces. If you ask how bright each of those little different pieces is, it's roughly a small dwarf galaxy. And so the contamination fraction in Sloan is incredibly high. And what my collaborator Mike Blanton did was go back into the Sloan database, re-reduce the photometry so that it actually puts galaxies back together that are relatively large in the sky. And now we can go and ask and study dwarf galaxies. And so that's sort of the innovation here. Okay, let me just start with the conclusion so that you can then go to sleep. I like to do this, and particularly in this talk I like to do this. So the conclusions are that ending star formation in a low-mass galaxy requires the presence of a more massive object. That is, whatever environmental processes are happening in low-mass galaxies are that control quenching are controlled by large, more massive galaxies. And so there's a threshold where this takes place, roughly, at least in the local universe, below about 10 to the 9th, again, something like the Large Magellanic Clouds. And so if you look in isolation, all galaxies below this math threshold are forming stars. We only find quenched galaxies, things that aren't forming stars, within about 4 Vera radius of a massive object. And this is an interesting number, why it's not 1 Vera radii, and it's actually 4. We'll talk about that. And then the new part of the talk, or the new work, is that despite looking at these isolated galaxies, despite the fact that they're isolated and they shouldn't sort of have been messed with all that much, we're finding that their gas fractions and that their baryon fractions actually vary fairly wildly, and we're trying to understand what the correlations are there. So let me try and prove those statements to you. And the way I'll do this, I'm going to start the introduction. It's more like a historical fashion in that kind of the way my work has gone. And so I'll start with talking about the Milky Way and sort of move outwards. So if we look at the Milky Way, most of the dwarf galaxies around the Milky Way are quenched. In fact, almost all of them are quenched. In the past couple of years, we found a whole bunch of new satellites. These are lower mass things than we can find beyond the Milky Way. But with the exception of the Magellanic Clouds, all of the galaxies around the Milky Way are quenched.
What's the visual radius?
About 300 kpc.
Actually,
Actually, I'll put that. Go ahead.
I just want to ask, so what do you mean by quenched? That
So I'll
it's not
define.
forming
Yeah. So I'll
stars,
define
or
what
that
I mean.
questions?
I will define what I mean by quenched.
Okay.
At this point in the Milky Way, that is, it's not currently forming any stars, and it doesn't really have any gas.
Okay.
But I'll be much more quantitative when we get into the work.
So does that mean it doesn't have molecular clouds?
No, it does not. Or at least to the limits that we can look for H1. No one really, because we don't see any H1. Why we'll look for CO? But they're very, very tight limits on the H1. So, for example, so this is the satellites around the Milky Way as a function of distance away from the Milky Way. For the nearest objects, and let's see if I get this right. Oh, good. For the nearest objects, the limits on H1 are something like less than 20 solar masses of H1. And so that's not a whole lot of gas. For all of these, the limits are quite low. And so there's sort of a dearth of objects here. This is the Sloan detection limits. If I change this and I ask which are the galaxies that are star forming, so red is not star forming, blue is star forming. You'll notice the Magellanic Clouds up here are fairly close in. They are star forming, but there's really strong evidence now that the Magellanic Clouds are coming in for the first time. They're infalling for the very first time. So we can sort of describe those off, and eventually those things perhaps will be quenched. And then there's this object out here, Leo T, which is a really fascinating object. It does have gas. The gas to stellar mass is sort of 50-50, and it seems to have been forming stars relatively recently, but it's actually beyond the Vera radius. So Leo T is off at something like 450 kpc. And so within the Vera radius, at least in the Milky Way, everything is quenched, with the exception of these two objects that are perhaps just coming in for the first time. We can move farther out, beyond the local group. So now this is absolute luminosity on the x-axis, and this is distance away from the local group on this axis. Again, color-coded, where blue is sort of star-forming and red is quenched. There's sort of a collection of objects up here at sort of 2 megaparsecs. This is the M81 group, so the most massive galaxy group around us. So sort of building up this story that quenched galaxies are only hanging out where a more massive galaxy is located. So quenched galaxies are preferentially found in dense environments, and this is not really anything new. What's interesting, if you look at the star formation histories of galaxies that have gas in the local universe, so all the galaxies that were on that previous plot, versus galaxies that are not star-forming, so dwarf spheroidals are not star-forming quenched galaxies. Dwarf irregulars have gas and are star-forming. Here is, as a function of time, the buildup of stellar mass. And what's interesting is that there's a huge amount of scatter in when stars were formed in these objects. But in general, there's really no difference between the quenched galaxies and the currently star-forming things, except in the last, sort of 100 million years. So again, this idea that perhaps these dwarf irregulars, things that are forming stars, have come into some environment and have been turned off. There's one exception. That's what I just said. There's one exception to this, which are much, much lower mass galaxies. And so this is kind of an aside. The faintest galaxies, the ultra-faint galaxies, which are almost 2 orders of magnitude less massive than the things that are in this plot, these turn out to have exclusively old star formation. And so their star formation histories would basically look like a step function. They go all the way up, and they formed all of their stars very early. That's not what we're talking about here, and I love talking about these galaxies, but I won't anymore. Okay, moving out beyond the local universe, or sort of, yeah.
So these are multiple galaxies.
Yeah, so these are all the galaxies that were in this plot.
Okay.
This is the ANK survey, so it's an HST study of sort of the local volume within about 2 or 3 megaparsecs, doing the sort of detailed star formation histories. Okay, so now moving out beyond just sort of the local couple megaparsecs, moving out to sort of the local volume, this same argument is phrased in a slightly different way. And so this is the classic color division between quenched galaxies, the red sequence, so now much brighter objects, and star-forming galaxies. And if you start to look at these in terms of their environments, so here again, absolute luminosity and color, if you look at quenched galaxies, they sort of form in 2 different regions. At high masses, you find quenched galaxies in dense environments, and at low masses, you also find these objects in dense environments. Sorry, this is density, so local density.
But a lot of the faint red galaxies have just obscured star formation.
Sorry?
A lot of the faint red galaxies have just obscured star formation.
Right, so that's why, so this is actually, that is the argument to use line diagnostics instead of color to define quenched galaxies, and so we'll get there in a second.
Okay.
So I actually prefer thinking about environment instead of, in this sort of density plot in the satellite central dichotomy. And so if you break galaxies up into just binaries, sort of asking what their local environment, you just say, what is a central galaxy and what is a satellite galaxy? So a satellite galaxy is a galaxy that exists within the virial radius of a bigger object, and a central galaxy is not. If you just break that dichotomy up, there's some really interesting work, and this has sort of been lots of papers in the last 2 or 3, maybe 5 years. My timeline is kind of messed up. If you plot as a function of stellar mass now, the quenched fraction, so that is the fraction of galaxies that are quenched, at the highest mass end, the quenched fractions are extremely high. For central galaxies, as you go to lower and lower masses, so the central galaxies are the black dotted line, as you go to lower and lower masses, the quenched fraction gets smaller and smaller and smaller. And then each red line, or each colored line is for a different parent galaxy, so a different parent halo, looking at all of their different satellite fractions. But let's just concentrate on the quenched, on the central galaxies for the moment. So as you go to lower and lower masses, the quenched fractions become lower and lower. And just to kind of put some numbers on it, so that in these numbers, the Milky Way is something like a few times 10 to the 10. LMC is 10 to the 9. So below this plot, SMC is sort of just hitting the blackboard. Yeah.
So the central galaxy have to have a satellite in it, or can it also just be a lone by itself?
A central galaxy is just the biggest thing that's around that isn't in somebody else's halo. So presumably, if hierarchical structure is right, everything has some kind of satellite, but perhaps it's too low mass to see, let's say, in the Sloan survey. Okay. So just to put a little theory on this, one question to ask is, so what is the quenching mechanisms different between satellites and centrals? So that is why is galaxies quenched. So this is basically the same plot, but now, again, talking about overdensities as a function of stellar mass. So why are galaxies quenched? So the idea here is that larger galaxies are quenched because of some sort of feedback mechanism. Let's say they maintain some kind of hot halo, they're able to turn their own star formation off. Smaller galaxies, if they're in some kind of environment, can be quenched because they live in the hot halos of a larger galaxy. But a small galaxy, the prediction here is a small galaxy that's by itself shouldn't be able to quench itself. That is, it shouldn't be able to turn off its star formation. And so really the question is going back to this plot, whether or not this central galaxy, this goes all the way down to 0 or not. That is, at what point can a galaxy that's on its own turn its own star formation off? So that's kind of what we went out to.
Run out of gas?
Well, so that's the question. So if I just take this line and I hit it all the way down here, does it hit 0 or does it sort of flatten out at some point? That's the question. Okay, so to do that, we need galaxies. Sorry?
I just said you're accreting, so even if you're quenched, you're still gonna accrete gas.
Or alternatively, know that the star formation rates, are the efficiency goes down, so it's possible that they just go through their gas very, very slowly. But that's the question. The question is, can this actually hit 0, or does it actually flatten out?
But to continue on my thought on this, molecular clouds, does that just mean there's less and less molecular clouds to form stars?
Can we hold that off? So we'll talk about the gas fraction, the gas stuff in the second half. So we'll get there.
But is the gas in molecular clouds or just sort of free all over the place?
So for lower mass galaxies, we can detect the H1. There have been very few CO measurements, and it's possible that at lower metallicities there's just a different CO ratio, and so it's actually fairly difficult to know what the molecular content is in these lower mass things. Okay, so what we need is a sample of lower mass galaxies, and we need a large sample of lower mass galaxies. And so this comes back to the Sloan Digital Sky Survey. The mass limit, again, on that slide before was not because lower mass galaxies weren't there, it was because this contamination fraction starts to kick in. So something like 30% of the dwarf galaxies in Sloan, in sort of the regular Sloan database, are essentially bad deep blends. So here's an example. This looks like a dwarf galaxy, or this looks like a lot of dwarf galaxies we're looking at. If you zoom out a little bit, it is clearly not. It's just sort of a star-forming knot along this sequence. So unfortunately, it turns out to be a fairly bad acronym. But the NASA Sloan catalog is taking the Sloan database, re-reducing it, reducing all the spectroscopic sources that are fairly nearby, that probably would be affected by this deblending issue that are relatively large in the sky. And the acronym is the NSA, which was turns out to be a less awesome acronym in the last couple of months than it was 3 years ago.
But you get a whole lot more hits.
Yeah. And so now every time I write an email to my collaborators, I'm worried that they're listening even louder.
They are.
They are. I know. All right, so this is just a reprocessing of the SCS database. It's actually a really rich database, and there isn't, I'm sort of advertising this a little bit. So here is a galaxy. This is the SDSS color image, and sorry. What happens here is, this is a foreground star. We're actually able to deblend the star out quite well. The previous reduction would actually include all the flux in the star. Here is a larger galaxy with, definitely a companion, and we're also able to resolve out those sort of things. So it's just a much cleaner sample. I'm going backwards. Now I'm going forward. Okay. So once you do that, we actually have a fairly large sample of low mass things. So this is this NSA database as a function of redshift. This is the absolute luminosity. This curve here is just set by the Sloan spectroscopy magnitude limit, the apparent magnitude limit. Turning this into distance versus stellar mass, so just basically interpreting those two, you can see down below 10 to the 9th, so down below LMC size things, we have a fairly large sample. So something like 10,000 galaxies to start playing with and to start extending that plot out a little bit. Okay, so now we're interested in asking, for this now low mass sample, what are the quenched fractions, and what are the quenched fractions for isolated central objects? So first, let me define what we talk about in terms of what I actually mean by quenched. Many people in the past have used color to define whether something is quenched or not. So they just say, something is red versus something is blue. Particularly for these low mass galaxies, we see a lot of objects edge on that actually look quite red that are definitely forming stars. That is, we look at the color, it looks fairly red. But when we look at the spectra, it's clearly got emission lines, and so it just means it's a dust-reddened disk. And so we prefer to use a spectroscopic survey, or a spectroscopic criteria for that. And so the main criteria that we use is the H-alpha equivalent width, which we can measure fairly robustly. This is the distribution for all, I can't remember, I think this is all the low mass objects, but it would look the same for all galaxies here. So this spike here is just for quenched galaxies that aren't forming stars, that don't have emission, and this is the distribution of star formation in these objects. And so we kind of arbitrarily, but pretty obviously, cut off at a certain equivalent width. We also use a second criteria, which turns out to not be as critical as I thought it might be. And we also ask, there's a line diagnostic, the 4,000 angstrom break. This is says something about the amount of recent star formation, when star formation actually shut off. You can see here, this is the 4,000 angstrom break. This is where quenched galaxies live. They have strong 4,000 angstrom breaks. These are the star-forming objects, and this changes as a function of stellar mass. And we have a D4000 break as well. So these two criteria have to be met. It turns out that this would have been almost sufficient for 99% of the galaxies. But I guess I'm actually not going to talk about them. But most of the objects that aren't forming stars don't have H-alpha also pass this criteria.
Is that real structure at 10 to the 10?
Okay, no, this is, I will get to this. This is where we have to artificially put our two samples together. Okay, so now we have whether something is quenched or not. We will also define an environment variable. And so this is sort of a proxy for the central satellite dichotomy. We actually don't have a group catalog. We can't actually say which of our dwarf galaxies are satellites versus centrals. We haven't done that work yet. That's going to change in the next couple months. But at the time, we wanted to do basically a cheap version of central versus satellites. And so what we do is we define the distance away from a massive galaxy, from a dwarf galaxy, and that'll be our environment parameter. So here you can see a fairly nearby object. This is a fairly massive Milky Way-like object. And this is why we need spectroscopy. There is one dwarf galaxy that's fairly close to this large object in this field. It's obviously going to be right in the middle because, whatever. So you need, the background galaxies, if you just had photometry, this would be a total disaster. But because we have spectroscopy, we know that that object is only about 70 kpc away. And so we define environment as the projected distance to the nearest massive galaxy. And I'll call this D host, that is the distance away from a massive host. For the satellite versus central galaxies that are beyond about a megaparsec, we'll be calling central galaxies, and I'll prove that in the next slide.
What's your definition of a massive galaxy?
It's above 10 to the 10. Okay, so now we have an environment variable. We also call galaxies quenched or not quenched. So let's just look at these in terms of their physical properties. So here I am plotting as a function of the host distance, just a couple of physical properties. So color, their equivalent widths in H-alpha, again this D4000 thing, where red is quenched galaxies and black are not. This is for the more massive objects. So this is between 10, a little bit larger than 10 to the 9 to 10, a little less than 10 to the 10. This is by definition my H-alpha cut here. This is also by definition this D4000 cut. You can see here the quenched galaxies, although they are tending to be red, there is some scatter down here, and those are these just reddened disks. Notice that as a function of the host distance, we have quenched galaxies that are going out to very, very large distances away from a host. This is for the more massive sample. Things are actually fairly different when we cut things a little bit lower mass. And so this is, again, the same three properties, color, H-alpha equivalent width, and D4000. But here, the quenched galaxies are all very, very close to their hosts. So it's sort of a hint of what's to come. I'm going to just skip that slide. OK, so now I can start plotting the quenched fraction as a function of distance away from their host. So looking at various different stellar mass, for the highest stellar mass, at least in the sample, the quenched fractions increase as you get towards a more massive host, but it also seems to flatten out and to sort of taper off at a certain, sort of 5% or 10% as you go farther and farther away. As we step down in stellar mass, again, it increases as you go towards a host, but this flattening off gets a little bit lower. And then once you get to about 10 to the 9th in stellar mass, it essentially goes down to 0 at about a megaparsec and a half away from a major host. And so I'm going to define, based on that plot, I'm going to define galaxies as field galaxies or isolated galaxies if they are farther away than 1.5 megaparsec. So all these things out here we're going to call isolated galaxies. Essentially, these are definitely central galaxies based on that.
Can you also compute the tidal radii for each of the host galaxies?
Yeah, so this is way, way beyond the tidal radius. So I'll show this as a function of viewer radius at some point. These things out to here, this is about 4 or 5 viewer radii. So well beyond where you might expect it. That said, it is interesting that it's flattening out. So this is a megaparsec and a half. The typical host size here is a Milky Way. The Milky Way is 300 kpc.
And if you went to higher mass, like say above 9.75, would you find that it goes out further? You know, it doesn't have to move your line out further? Or?
Yeah, the problem is that this dehost thing breaks down, and you have to go back into central satellite. So if we went back into central satellite, then yes, the quench fractions increase as you go to higher masses. Right, so trying to compare to more massive things. So we have these two different environment variables, or environment things. We have dehost, this distance. We also have the central satellite thing. And so what we did is we kind of Frankenstein two samples together, our lower mass thing and our higher mass. At higher masses, we were using Jeremy Tinker's group catalog, where we played a little bit to try and make these two samples match. I'm not actually going to go into how we played with them, but I can talk about that in a bit. What this allows us to do is plot both, as a function of stellar mass, we can now plot the quench fractions. So this is basically the plot that I showed before. So again, stellar mass as a function of quench fraction. The blue points were that dashed black line a couple plots earlier, where they were able to get down to something like a few times 10 to the 9, but it didn't actually hit 0. We can now extend this out much further. So now we can actually ask, does this actually hit 0? And in that, in a linear plot, it's kind of hard to tell, so let's talk the same thing, but plotting it in log space. And indeed, this thing goes down fairly low, and then we actually have upper limits. That is, out of below this last data point, below 10 to the 9, none out of the 2,951 galaxies that are below this were quenched. That is, they were all star forming. And so these are all upper limits. The upper limits get worse simply because as we go to lower and lower stellar mass, we have fewer and fewer galaxies, so the number statistics get lousy. So our upper limit on the error bars just gets increased. But below 10 to the 9th, it's a fairly robust result that we just see nothing that is forming stars.
So is the fact that the continuum, I would think, is dropping on top of what you see the H alpha, is it just you're running into the noise of the continuum to be able to see an H alpha line?
No, we would absolutely see. So for all of these, for all these objects, we see, these are very, very bright objects. Signal to noise and that sort of thing is that we're way, way out of that regime. Okay, so that means that there's some kind of stellar mass threshold, at least at z of 0, below which we aren't seeing quenched galaxies in the field. This is interesting. So the first thing to ask is just, are we somehow biased? Did we somehow screw up? So let me just spend a slide on the ways we might have screwed up. There is one bias that worries me a little bit, although I think we're okay, and that is we've really only, Sloan has a very, very, has a surface brightness limit, and we know that lower mass galaxies are lower surface brightness. The surface brightness for Sloan is complete, so this is the completeness as a function of central surface brightness. The 50% roughly completeness limit is at about minus 23.5 in R. 90% completeness is about 22.5. If you look at the local group, if you look at the Milky Way satellites, this is a function of absolute luminosity. These are all the Milky Way satellites, and I guess that's the Milky Way up there. This is the surface brightness cutoff. So we wouldn't see a lot of the dwarf galaxies in the Milky Way, all the really low luminosity ones, except that we're talking about 10 to the 7 to 10 to the 9. And so we're actually talking about this regime here. So the fact that we wouldn't see any low surface brightness things up here, in the local group at least, we are just on the edge of being able to detect all of those galaxies. So I don't think the surface brightness completeness is an issue, at least for these stellar masses. If we wanted to push deeper, it's going to be a huge problem for Sloan. We need a different database. Another concern is perhaps we're just missing low surface brightness things that are in the field. So this is the distribution of surface brightness for this is for the star-forming objects. This is the surface brightness completeness limit, so yeah, it makes sense that we're not seeing that many objects that are lower surface brightness. This is for the quenched objects, so let me expand that up. So the quenched and the star-forming surface brightness distributions are very, very similar. And these are all for satellite objects. We don't have any quenched things in the field, so we can't compare in the field. But at least here, we aren't seeing a real difference in the distribution. So I don't think we are actually missing any quenched galaxies in the field unless there's some really perverted distribution and that they're only really weird low surface brightness objects in the field. I don't think that's likely. Okay, so now I can start asking questions about this population. And so here, this actually goes back to your question. So this is now asking, what is the distribution of quenched versus star-forming galaxies away from their hosts? So here's for the quenched satellites, and this is all for galaxies that are less than 10 to the 9th now. So if I just ask for the quenched galaxies, 90% of the galaxies that are quenched live within 2 viro radii of their host. And we see essentially 99% out to 4 viro radii, which is fairly interesting. And this is radically different than the star-forming sample. So the star-forming sample, within 2 viro radii, only half the galaxies are living, and you can see a huge distribution out in this direction.
So what's the one guy that's way out there at 8?
Yeah, I have looked at him and I forget. I forget who he is. I mean, yeah, I don't remember. I'm not sure the viro radii are all exactly right on as well. Yeah, but that's one object. So based on this plot, I can make the statement that dwarf galaxies require a massive host to quench star formation. That is, all of these things are really close to a massive host. What's interesting is that this process is extending out to 4 viro radii. So you might think that whatever environmental process is going on, would happen within the viro radius, within the sort of gravitational influence of the object. And it's clearly out to much larger distances than you might expect. If you look at the Milky Way, this also is interesting and is consistent with what we see in the Milky Way. So if I look in the Milky Way, this is actually goes back, this is the H1 masses. This is distance away from the Milky Way, and this is the total gas fraction, so the amount of gas in galaxies. Most of these things in here are upper limits. Now this is a log scale, so stellar mass of 1 to 1 would be all the way up here. All these objects up here have a fair amount of gas. These are the dwarf irregular things. This is all well beyond the viro radius, and so all the things that have gas are beyond the viro radius, 1 viro radius, with 2 exceptions, which is really quite interesting. So Cetus and Tucana are quenched galaxies. They're at 2 and 3 viro radius away from the Milky Way. So the question is, what's going on here? Why are those things quenched? Before this work, there were 3 possibilities. One is that there's some kind of long-distance quenching going on from the Milky Way beyond the viro radius. Another idea is that perhaps these things are backsplash galaxies. That is, these objects used to be farther in, closer into the Milky Way, and have just come out. And then there's a third possibility that perhaps these were just some part of a quenched field population, so that there's quenched galaxies out in the field, and they just kind of happen to come in. What's nice about this work, and it's a tiny thing, but we can at least cross that out. So we know that in the field we do not see galaxies with those stellar masses that are quenched. So they couldn't have come in from much larger distances and come back. Now we only have 2 possibilities to deal with: long-distance quenching or some sort of backsplash galaxy.
And then can you predict their orbits if it's a backsplash?
Yeah, absolutely. So that's what this super messy plot was trying to do. So this is Catherine Johnston and one of her students were looking and asking, what are the fraction of galaxies that are at large radii that have been into much, much larger, smaller radius and then have come out, and what do their orbits look like? And sort of walking through this just terrifically awesome mess. Maybe I won't even do that. The idea here is that these are, they're looking at the dark matter halos, just dark matter halos in the Via Lactea simulation. These are galaxies that are bound within that single structure. These are all galaxies that are coming in for the first time. And these are all the halos that have been within the viro radius and have come back out. And so they find something like 10% of the satellites that are between 2 and 4 viro radii have at some point been previously in. So if I look back at that previous plot, 10% is roughly 2 or 3 satellites. And so it makes sense with this Cetus and Tucana being backsplash galaxies, at least in the simulations. And these numbers also agree with what we're seeing, that sort of 10% or so of the quenched galaxies are beyond 2 viro radii.
You get a proper motion eventually?
Yeah, it would be awesome. So, so far, looking back here, there's been proper motions reached just recently for Geha 1, which is unbelievable. These things are a fairly large distance farther than that. But I believe the Space Telescope people have magical powers, and I am sure they're going to be able to measure proper motions of these things given a long enough baseline.
So how do you know whether it's the first time in or if it's the third time in?
It's a good question. We have to have the orbit, so we have to measure those proper motions. So if we
You
knew,
only have one data point then, right?
so if I know the 3D space motion of that object and I know the mass of the Milky Way, which is always a problem, you can back out what the orbit is and you can say, you know, sort of what is the orbital history of that object.
But you don't know how many orbits it's done.
So, I mean, it depends on how well you believe your backwards integration in the mass of the Milky Way is a function of time. So, you know, I actually think doing this statistically, looking at the quench fraction as a whole is sort of the way to get at the question of backsplash stuff. Okay, so now we have the sample of isolated galaxies. We know they're all forming stars, so I wanted to concentrate a little bit on these isolated objects. And so this now gets into the more preliminary part of the talk. None of this stuff has been published, and we're still kind of working on the paper. So we now know down to 10 to the 9th, if you look at a galaxy that's less massive than that, it is definitely forming stars. This isolated sample is interesting. It's unique in the sense that we know that environment is not playing a role, at least doesn't seem to be affecting these galaxies so much. And so this gives us an opportunity to study the intrinsic properties of galaxies, of these lower mass systems. And I say intrinsic just because we know there's going to be processes, but at least it's not as bad as the satellites around the Milky Way. These things are all forming stars. For the few things that people have looked at, they have a fairly significant gas component. And so to really complete this story, we need to have the gas components of these objects. And so I have a student who's working on getting the gas fractions and measuring the gas for that. So I'll show a couple preliminary results on that. The H1 profiles of these objects are great. So if you get a single dish H1 profile, you get two things out that you don't get immediately from the optical data. So these are two profiles. This is a function of velocity or frequency and flux. We immediately get the gas mass out, but for free, essentially, we also get the dynamical masses out. That is the line widths probe much larger out in the disks, presumably, of these galaxies. And we can make some assumptions and call that a dynamical mass. And this is relatively cheap. It takes, for these objects, it's only a couple of minutes exposure time with big telescopes. A lot of this work for slightly higher mass galaxies has been done with the Alfalfa survey. So this is a survey that's led by Cornell, Martha Haynes, and Riccardo Gimenelli. This has all been done with Arecibo, which is a gigantic radio dish, and you can survey a lot of the sky. Alfalfa surveys a fairly large region. They have lots and lots of galaxies, but for this stellar mass below 10 to the 9th, which is what we're really interested in, they actually have very, very few galaxies. And so Jeremy Bradford, who's a second-year student now at Yale, for his PhD thesis, we're basically trying to fill in this lower mass region. So basically do what Alfalfa has done, but just at an order of magnitude or 2 lower masses. I have a minute, good, so I'll do that as a side. As part of this work, we've actually done something that is slightly devious. I'm teaching an astrophysics research methods class. And last week, we added to Jeremy's sample by taking a whole bunch of undergrads down to Arecibo. And we suggested this as one of their projects. And they were supposed to design all these observations on their own and implement the observing. And all of them, 3 out of the 4 groups picked this project, so to find a whole bunch more low-mass galaxies. And so it was completely autonomous, but we were strongly encouraging them to do our science. And it worked. So it was actually incredibly successful. I've talked to some of you guys in the audience about getting undergrads up to speed in terms of understanding radio, understanding how to design observations and implement observations. And in the next week or two, they're actually doing the data reduction as well. So it's been a fun. It's an interesting question. I don't know. There was one project that, if it had worked, we absolutely would have written a paper together. This, it's like 4 or 5 objects out of 100, so maybe, maybe not. Anyway.
That was acknowledged.
And they'll definitely be in the acknowledgement. Okay, so here is looking, and I'll come back to this plot in a moment, but so the baryon fraction, so this is the gas plus the stellar mass as a function of mass. This is just to show you that the blue points are alfalfa, and the red points are what we're filling in. So we're just trying to fill in this lower mass region. I'll come back to this plot in a second. All right, so let's think about gas fractions as a function of, let's say, stellar mass. So this is the combined data set of this alfalfa as well as the stuff that we have filled in. As a function of stellar mass, so the Milky Way is sitting over here somewhere. This is just a fraction of gas to stars. So something that has a gas fraction of 1 is a completely gas galaxy, and a fraction of 0 means there's only stars. It's completely quenched. So there's some interesting things here. So first of all, there's kind of a region where galaxies tend to avoid. That is, for a galaxy like the Milky Way, it's fairly good at turning its gas into stars. And as you go to lower and lower mass galaxies, they become essentially just more and more lousy at turning gas into stars. What's really interesting, so the star formation efficiency is lower in lower mass galaxies. Where this trend hits 1, or basically where galaxies populate the entire range of gas fractions, is also right at this 10 to the 9th stellar mass that we were talking about earlier.
So you're measuring the gas mass from H1, just all ionized, and you just don't.
We don't. Yeah, I don't deal with ionized gas. So most of the gas is probably in some sort of neutral component. We don't know what fraction is in ionized, but we don't account for that. We don't know what it is in the Milky Way either. So ionized gas is not accounted for in any of this. Okay, so now I can ask, this is for galaxies in all environments. I can now ask, what are the gas fractions for things that are isolated? And so here, this is just arbitrary, where I've only done this isolated criteria. Start to see that there is some indication that the isolated things are avoiding some of this region. And so what I'll do is I'll take these red dots, I'll take all the low mass galaxies, and again plot them as a function of this D host, this environment factor. So here, I'm defining things as isolated. So as I said, it's about 1.5 megaparsecs. As a function of D host, and you can see that the isolated things, as you might expect, all have gas. They're all forming stars. And it seems like there's some sort of lower threshold of about 20% gas. But what's pretty interesting, to me at least, is that there's a huge range in scatter. And this is a fairly small region in stellar mass. So this is everything below 10 to the 9th down to 10 to the 7th. So this is dominated by things that are sort of 10 to the 8th and more massive. But there's an enormous range in scatter. And so the next couple of questions are, what is controlling that scatter? Is it intrinsic, or is there some interesting property? And so that's where this definitely gets a bit fast and loose.
What's your typical observational error on the gas fraction?
That's a good question. It's pretty small, actually. And in fact, that's where alfalfa, there are a lot of points in alfalfa that are down at sort of 10 to the 9th, and they're 100% error bars. So, I'll just go back real quick. These are actually typical H1 profiles. And so you can see the signal to noise there is actually pretty good. And we're doing, long enough exposures. They're short exposures in some sense. They're only a couple of minutes. This is some of the worst profiles that we have. So the stellar mass is definitely 20% errors, and the gas mass is around that as well.
Interesting that most galaxies follow, pretty thick band there, and then there's, I guess.
And then so it's basically there's some relations, and then there's an explosion.
Yeah.
And that in my last actually 2 slides, that's the sort of conclusion we're finding, is that there are interesting relations. There's a baryonic Tully-Fisher, and then below, around 10 to the 9th, 10 to the 8th, there's just an explosion, and things become fairly stochastic. So looking just at the isolated galaxies, and asking, is there any correlation of some property with gas fraction? And this is all preliminary in the sense that this plot was made this morning. And the reason is that we just have gotten our sample large enough where I can actually do these sort of plots. And so this is now gas fraction for these isolated things as a function of the equivalent width, looking at the specific star formation, so essentially the star formation of the H alpha divided by the stellar mass. In the H alpha, I don't really see a particular trend with gas fraction. We might see something with specific star formation rate, which is maybe perhaps interesting. Whereas the high gas mass things might have slightly higher star formation rates. And so these are the sort of questions we're asking. Jeremy's putting a paper together in the next couple of months on this. 2 more points, I think, before I end. So we can also now put the gas and the stars together and look at the baryon fraction as a function of total mass. So again, this is our sample and the alfalfa sample. These are for only isolated galaxies. So only isolated objects or central objects. This is the Tully-Fisher relation, and so if all galaxies were born with exactly the cosmic baryon fraction, this should be a very, very tight line. Things are fairly tight at high masses, and then all of this scattered here is actually real. So these are all low mass galaxies, but they are very, very secure measurements. And in fact, we have about 30 or 40% more data points, but they have a little bit larger errors or have a little bit larger inclination effects. And so this is actually our most secure sample. And so the scatter here for isolated galaxies seems to be real, that there's a real scatter in the baryon fractions, which is really quite interesting. We have to think about that a little bit more, and I'll be interested.
In your age or something like that? What could it be?
So my hunch at the moment is it might be some this kind of mass accretion history. So these things are isolated, but they still have some kind of accretion history. And so it will actually be up to sort of the Duchamp and the simulators to sort of help us guide. Yeah. So I actually don't quite know how to test it. At the same time, we're still in the early stages of trying to correlate everything with everything.
Do you expect any of these galaxies to ever have been AGNs?
That's a great question. So we have looked in the NSA. We have actually looked for AGN. This is a paper by Amy Raines and Jenny Green. The three of us. I kind of cheered from the sidelines, and Amy did a lot of the work. In this sample, there are 150 AGNs, and she did this by going through the Sloan spectra and re-reducing it and doing a VPT diagram. So below 10 to the 9th, there are 150 new AGNs. The paper was just, hey, there's a bunch of AGNs. We haven't done the real work that I'm interested in, is to ask, what is the AGN fraction as, let's say, a function of stellar mass? And that requires understanding what is the luminosity AGN you could actually see given the SDS fiber and the size of the galaxy. And that's a bit of work, and that's something we haven't done yet.
And Arecibo can't say if it's radio loud that it's an AGN?
I only know how to do H1 observing with Arecibo.
Okay.
Are AGN loud in radio? Yeah, the AGN radio loud. I don't know is the answer to that. The AGN sample we've really just started to think about. And I honestly, if you'd asked me a year ago, I'd assume there aren't any AGN in these objects. That's not a true statement anymore, which is interesting.
So just a comment for getting back to what you were asking. So the scatter that you're seeing, this sort of reminds me of the talk that Janice Lee gave here a couple years ago. She was talking about how as you go to lower mass galaxies.
Yeah, these are the same objects.
Okay, that's what, yeah.
I mean, they're not the same objects, so we basically start at 10 megaparsecs and go out, because within 10 megaparsecs, with the distances, you have to just do different techniques. Her stuff is all within 10 megaparsecs, but they're the same stellar masses. Yeah. So we just have larger statistics.
Yeah, so she was just finding that the star formation histories are much more stochastic and have a lot more bursts, as you put it.
And yet, at the same time, everything we see is star forming. So there's this interesting tension to me between you have bursty star formation going on, and yet we don't see a single thing that's off.
Yeah, but that's because so you're saying that the things that are near more massive galaxies are quenched.
Yeah.
But it's not necessarily that they're near more massive galaxies. It's because it could be because they're in more massive parent dark matter halos. So you're looking at things that are in lower mass halos. And so quenching, I don't think quenching is due to AGN. If it's due to something like the halo mass, then that's entirely because these are just in lower mass halos.
I agree with that.
And this transformation rates as a function of the sample here is very crazy like this.
Yeah, so the star formation rates, this is the star formation, so these are specific, but it's basically the same. So they're varying, and this is all over the place essentially. Basically the H alpha flux, it goes from greater to 2 out to 500. It's huge.
Because these are such a low mass that handful of supernova.
Yep.
A couple of bursts, so they might be still on at given point in time, a couple of previous bursts.
Yep. So the next couple of steps are things like we want to do IFU of some of these objects, the kind of interesting outliers on these trends, to look at where is star formation happening, so what Janice has that we can't is to get the really, the star formation history, look at the individual stars. We can't do that. Where we do have, we win is we have statistics. And so we can ask, for these crazy outliers, do we see something different in, their star formation rates, or, where star formation is happening within the galaxy, those sort of questions. Okay, my last slide is just talking about these objects in terms of using them to test cosmology. So we now have an isolated sample. I actually think we can connect our masses, that is the line widths of these objects, to their dynamical masses, that is their halo masses. And we can ask essentially the same question that people have been doing with the missing satellite function, basically asking the dwarfs missing around the Milky Way. We can do the same thing, but just asking in an isolated environment. So doing the same sort of test. And so just comparing the number density of low mass galaxies in isolation to predictions. And so here is something that Mike Blanton and I published a couple years ago. So this is cold dark matter mass function, and I forget what the warm dark matter particle was in this plot. This is anyway, that line has a lot of problems. But the data points have a lot of problems as well. So this last data point, which is really interesting and tantalizing, there are 12 galaxies in that data point. So 12 low-mass isolated galaxies. And so we were really interested in both increasing the numbers and pushing the numbers down. With this sample, we can now do that. So this is Jeremy's sample. This is just as a function of the halo mass, the velocity mass, the number of galaxies we have. Notice that last bar there is 50. So we can triple the number of data points and actually push this down a little bit as well. And so this is paper 2 in his thesis. I think the hardest part of this is actually going to be the what to test against, but that's another conversation. Okay, so coming back to the conclusions. So just to reiterate, so ending star formation in dwarf galaxies requires the presence of a more massive galaxy. And these are the 3 points that I made right at the beginning of the plot. So there seems to be a stellar mass threshold below 10 to the 9. Very interesting to see whether that threshold changes as a function of redshift. There's a prediction that it should, and I actually think the data are out there to do this. Quench galaxies seem to only exist within 4 Vera radii, but it's interesting this number of 4 and not 1. And that we do seem to be seeing real stochasticity happening below this threshold, in both in the gas fractions and the baryon fractions. And I will end it there.
So I thought, so you had a plot early on where you were basically saying that every satellite in the Milky Way, other than Magellanic Clouds, is quenched.
Yeah.
Star formation. But then later, when you showed as a function for the so-called quench fraction for stellar mass bins,
it went up to something like 30% or 40%.
Yeah, exactly.
Yeah.
So it suggests that most satellites.
So I have 2 answers to that. One is that that fraction is for a mixture of halo masses, of parent halo masses. And so there are more massive than the Milky Way and less massive. And so we really should split that out as a function of parent halo mass. Okay. What's also interesting, and this is a different project, is asking whether or not the fraction in the Milky Way is in fact right. So another project is looking, this is with Risa Wechsler, we're looking for satellites around Milky Way analogs. We've gotten follow-up for 1 object. We have found 2 satellites at this 10 to the 8th level. Both of those are forming stars, and they're really, really close into their parent. So it is unclear whether those fractions are because of halo mass or because the Milky Way is actually weird, or it might be both. Okay. Yeah. But yeah, so we've been concentrating on the isolated fraction for the most part, just because it's like life is easier there. Yeah. And the next thing is to think about the satellites. Okay. Cool. Yeah.
Do you know the approximate dark matter content of these 9 solar masses?
So if I just take the stellar mass to halo mass relationships, it's 10 to the 10.5, 10 to the 10.5, 11. Whether or not the stellar mass halo mass relationship works down at those, so this is using like the Baruzzi scaling. Whether or not that works, down at those masses is up to somebody else.
Yeah, because I see the same scatter in my star formation array in my simulations.
Mm-hmm.
And it's at 10 to the 9, but it's 10 to the 9 dark matter.
Yeah, so these are definitely more massive than that.
So your 10 to the 9 is stellar mass.
Yeah. Yeah, so these are things that have circular velocities on the order of 60 to 80 kilometers a second.
Well, I just want to know whether what Allison said, what you said, are the same or not. Maybe you, Sean, can help. Is it that the presence of the more massive neighbor somehow stops the star formation, or is it the fact that it's in a bigger halo? Are those the same, or are those different effects? I imagine one is kind of like some kind of coming in and bashing around, and the other is just, it's the same or not.
So we probably should talk about it. I think it's because these things are coming into a bigger halo. Sound the same to me?
Strangulation
Okay.
kind of thing, where the gas is
Okay.
preventing from.
Yeah, it can be. Depends on what mechanism.
Yeah, so none of this, absolutely none of this speaks to the mechanism, really.
I just want to know whether those two cases are the same, and I hear you say.
They can be, it depends on what you want. If it's some kind of like feedback from galaxies, then yeah.
Well, that's what I was thinking you were saying here, is that's the feedback, it's the wind, the stellar wind
But
coming
maybe,
out of
maybe
the.
it's the halo.
Well, the gross position, but for the paper that you said, suggested surround pressure stripping.
So it is interesting to ask. So this is another question we wanted to ask. So take all of the galaxies that are star forming that are just on the edge of the Milky Way or a big galaxy, and ask in the simulations what are the orbits that how far do those often come into the center? And so is it 100 kpc or 50 kpc? Because if you're going to have ram pressure stripping, you need to get them inside of 100. And to me that seems implausible, but we actually haven't done the math.
I mean, I've heard some people say that ground pressure stripping is not really efficient until you get to more massive halos.
Right.
And radiation pressure can go much further down.
But in some sense, knowing that there aren't quenched low mass things in the field now, that means that one of the big questions has now been crossed off. We know that doesn't happen, and so it has to be something in the environment. Yeah.
So I want to, I apologize, this is a silly question. I want to get back to this idea of the gas fraction, what that you're measuring H1, and whether you know how much of the gas is ionized or not. Is there any reason to think that at low galaxy masses that perhaps you have a bottom heavy IMF, so you have fewer high mass stars, and so you have fewer ionizing photons, and so you end up with more H1, or the opposite case? I'm not, like.
Those are good questions.
Is there any?
So I don't know of any observations that say what the ionized fraction is in these sort of objects. Maybe LMC, SMC is where we could look. In the SMC, we know the IMF is pretty normal, and these are the same masses, and so I don't know. Down to way lower mass, the IMF is different, but that's a different talk.
Sure.
And so I don't know quite how to do that. We've thought about looking for background quasars. We have enough of these objects that some bright background quasar's got to be around one of these. And every time there's an HST cycle, I go and I look, and there isn't one that's close enough and bright enough. And so it's a good question, but I don't quite know how to get at it observationally.
Are there other diagnostics that can tell you anything about the ionization, the ionizing field of the galaxy?
I don't know the answer to that. I would love to know that.
Any other questions? Okay.
Thanks.
Dr. Geha's work is focused on near-field cosmology, mostly dwarf galaxies, so satellites around major galaxies like the Milky Way, ultra-faint galaxies, and by studying these systems, she can actually measure the entire mass function of these different galaxies. Something we can't actually do very well here in the Milky Way, so she's actually learning about the stars in these systems in a much more precise and fundamental manner than we can do here in our own system. So today she's going to be talking about quenched dwarf galaxies in the field. Please take it away. Thank you very much.
So I'm delighted to be talking in the Marlar room. I think that seems appropriate. Just take one letter off.
I told her if you gave us $5 to change.
This is how I change slides?
Yeah.
Good. Okay, thanks. So it's a pleasure to talk to you today. I've had some great interactions today already. I'm going to be discussing something actually more massive. I like dwarf galaxies. I study lots of dwarf galaxies. I often talk about very, very low mass galaxies. So the satellites around the Milky Way, and particularly the ultra-faint satellites around the Milky Way, things that are these tiniest galaxies in the known universe. Today I'm going to be talking about...
Okay, well, thank you all for coming. It is my great pleasure to welcome our speaker today, Geha, who's coming from Yale. Our second visitor from Yale this quarter. Marla is extremely prestigious. She's won, I think the only person I know has won prestigious postdoctoral fellowships in 2 countries. So the Hubble Fellowship here and the CASS in Canada, which she took down at Victoria, which is not a good serve, very cool. Since she's gone back over at Yale, she's also earned the Sloan Fellowship. She's been named on the Whitney Humanities role, which is impressive for scientists to be awarded for humanities things, which is really great. And I think the most amazing thing is that she's also been named the Brilliant 10 in Popular Science, which is probably why if you go on Amazon, you can find a full wall picture that you can order for $170 to put in your living room.
I'll give you a discount price.
All right. She did her graduate degree at Santa Cruz, where she was also distinguished there with Whitfer Prize and Presidential Dissertation Fellowship, and only got the 45+5 at UCSC. So apparently they're not as selected.
Are different photometric objects. And so what's happened is the pipeline has decided that this large massive galaxy is broken up into a whole bunch of different pieces. If you ask how bright each of those little different pieces is, it's roughly a small dwarf galaxy. And so the contamination fraction in Sloan is incredibly high. And what my collaborator Mike Blanton did was go back into the Sloan database, re-reduce the photometry so that it actually puts galaxies back together that are relatively large in the sky, and now we can go and ask and study dwarf galaxies, and so that's sort of the innovation here. Okay, let me just start with the conclusion so that you can then go to sleep. I like to do this, and particularly in this talk, I like to do this. So the conclusions are that ending star formation in a low-mass galaxy requires the presence of a more massive object. That is, whatever environmental processes are happening in low-mass galaxies are that control quenching are controlled by large, more massive galaxies. And so there's a threshold where this takes place, roughly, at least in the local universe below, about 10 to the 9th, again, something like the Large Magellanic Clouds. And so if you look in isolation, all galaxies below this mass threshold are forming about a little bit more massive dwarf galaxies. That's maybe not small, whatever. Galaxies that are sort of the mass of the Magellanic Clouds are a little bit smaller. And I'll be talking about some work that we published just about a year ago, and then some follow-up stuff in the last year. So the last half of the talk is super preliminary, which is always fun and kind of dangerous. The first half of the talk is completely summarized in my title, so I should just be done and I'm gone. We found that there is an absence of quenched galaxies. That is, there's an absence of things that are not forming stars in the field. That is, if you go out into isolation and you find a dwarf galaxy, it is always forming stars, which is a fairly interesting result. And so my hope is that I can convince you of that, at least in the first half. The innovation, or the reason that this work was able to be done, and it hasn't been done before, is not that these dwarf galaxies are difficult to find. In fact, we see 10,000 low-mass galaxies in the Sloan database. The problem is that in the Sloan Digital Sky Survey, it just wasn't, the data pipeline was not optimized for nearby objects. And so if you go into the Sloan database and you ask for a bunch of dwarf galaxies, this is not a dwarf galaxy, this is a massive object, all the blue circle stars, we only find quenched galaxies, things that aren't forming stars, within about 4 Vera radius of a massive object. And this is an interesting number, why it's not 1 Vera radii, and it's actually 4, we'll talk about that. And then the new part of the talk, or the new work, is that despite looking at these isolated galaxies, despite the fact that they're isolated and they shouldn't sort of have been messed with all that much, we're finding that their gas fractions and that their baryon fractions actually vary fairly wildly, and we're trying to understand what the correlations are there. So let me try and prove those statements to you. And the way I'll do this, I'm going to start the introduction, it's more like a historical fashion, in that kind of the way my work has gone. And so I'll start with talking about the Milky Way and sort of move outwards. So if we look at the Milky Way, most of the dwarf galaxies around the Milky Way are quenched. In fact, almost all of them are quenched. In the past couple of years, we found a whole bunch of new satellites. These are lower mass things than we can find beyond the Milky Way. But with the exception of the Magellanic Clouds, all of the galaxies around the Milky Way are quenched.
What's the visual radius?
About 300 kpc.